So this is the first video from chapter 27. We're going to talk about capacitors and capacitance, and this is covering what's in chapter 27-2 of the textbook. Okay, so first off, before we get to capacitors, you can think a little bit about how you would store charge, right? So we've got positive charge and negative charge. So the general idea, if you want to store up some charge, is you take two conducting sheets of some sort, so typically made out of a metal, and you separate them by an insulator, right? And you need this separation or else the positives and negatives will just attract each other. So an example of this is the Leyden jar. So these were actually used by Ben Franklin and others in the early studies of electricity. And basically, so you've got a little glass jar, there's a metal thing on the inside, there's a metal thing on the outside, and you store negative charge on one, positive charge on the other, and the glass, the insulator between them, keeps that separate. So you can actually use this to build up the charge, different charges on each plate, and you can actually build up a potential difference. And another way to think of this is, right, so it's going to take some energy to build up this charge. So you're storing electric potential energy in these Leyden jars. And in the bottom right here, so you can see back in the day, so people actually used these things to store charge, and they actually made these gigantic arrays of these Leyden jars, and you can actually build up quite large charges and quite large amounts of electric potential energy. Okay, so that's the basic idea of storing charge. And this leads to something called the capacitor. So for the simplest case, so a capacitor is just two parallel conducting plates separated by an insulator. And for now, we're going to assume that insulator separating the plates is air or vacuum. Towards the end of the chapter, we're going to talk about what happens if you put an insulating material there. So that's basically what you see here. So in the picture from your textbook on the bottom here, right, so in the middle is this parallel plate capacitor, right, so you've got plate on one side, plate on the other side, and we're going to build up opposite charges on each plate. So when you charge these things, so you end up with equal and opposite charges on the two plates. And the nice thing, so we talked about the electric field. If you have two insulated or two charged plates and the electric field is constant in between them, as long as you're not close to the edges, which means that the potential difference between the plates is the same everywhere, which is convenient. So since the potential difference is the same everywhere between the plates, we can define something called the capacitance C, and that's a constant of proportionality that tells us about the stored charge. So this is how capacitance is defined. So the charge stored, and again this capital Q, it's the absolute charge stored on one of the plates, right, since the net charge is 0. So Q is defined as the capacitance times the potential difference between the plates. So in SI units, well, capacitance has to be charge over potential difference, so coulombs divided by volts in SI units, and a coulomb over a volt is named after, as usual, a dead white guy, so Mr. Michael Farad, or Faraday, so it's called a farad, abbreviated capital F. Okay, so now a capacitor, well, it's storing charge, but it's also storing energy, right? So we decided they're storing electric potential energy. And for electric potential energy, remember in general, the way we calculate electric potential or potential energy of any kind, it's related to the work done. So, and again, from last chapter, we talked about potential difference. So electric potential difference is related to electric potential energy is related to the potential difference, delta V, times the charge, dQ, and we have to do this integral. So again, you're imagining you're charging up the capacitor, so you start off neutral, and you're slowly moving one charge from one plate at a time, from one plate to the other, one charge at a time. So delta V, as you're building up charge, this delta V increases. And so delta V for our capacitor, the way we define capacitance is Q over C. So in the middle here, so this is the integral we have to do, integral Q over C dQ. And well, this is just going to be Q squared over 1/2 Q squared over C. So that's the energy stored in our capacitor, 1/2 times the capacitance times the potential difference squared.